Hello, welcome to lesson 6. In this lesson, we are going to look at the measurement of the focal length of a convex lens. There are a number of methods that we can use to measure the focal length of a convex lens. Method 1, we shall use a distant object. So a distant object, such as a window or a tree at a distance, or maybe it can be a building at a distance, is focused onto the screen using a convex lens. So it will be like that. So rays from that distant object, of course, will fall onto this convex lens which has been mounted on a lens holder, and then it will converge to the screen. So we need a sharp image of that distant object onto the screen. Now, to ensure this, we need to first of all note that this experiment, you do it where there is limited light, so that we don't have interference of other light rays coming onto that screen. So what we do is that to make sure that the room has limited light or is quite dark, so that we can have a sharp image formed on the screen, a sharp image of the distant object formed on the screen. So in other words, we are going to adjust this screen so that we get a sharp image on that screen. And after that, you're going to measure the distance from the screen up to the center of this convex lens. So we need the center point of this convex lens. So we measure that distance f, and that distance is going to be the focal length of the convex lens. Let's look at method 2, that is using a plane mirror, and the non-parallax method, or what we call the no-parallax method. In this method, we shall use a plane mirror. So we shall get a plane mirror, place it on a table with the reflecting face or the reflecting surface facing upwards, with the reflecting surface facing upwards, and then we shall place the convex lens on top of the reflecting surface. So it will be like this. And then after placing it here, we shall clamp a pin horizontally above the convex lens, such that its apex or its tip is along the principal axis of that convex lens. Along the principal axis of that convex lens, this tip must be along the principal axis of the convex lens. When you have achieved that, we are going to move this pin vertically, that is up and down, until when its image, that's the image of the pin, coincides with the pin by the no-parallax method, And when we have achieved that, we are going to measure the distance from the pin up to the convex lens. And that distance f, which has been measured, is going to be the focal length of the lens. Let's look at method 3, using a plane mirror and an illuminated object. So here we are still using a plane mirror and then an object which has been illuminated. So we shall get, our screen still will be at the same position as the object, of which the object here we shall use cross wires. Cross wire is going to be the object, and then the screen will still be on the same point, because the cross wire will be in a hole which is on that screen. So the screen and the object are going to be at the same position. Then we shall also need a plane mirror, and then our convex mirror will be mounted on so our convex lens is going to be mounted on the lens holder. So it will be something like this. This is the setup. You'll have your convex lens on a lens holder, a plane mirror, and then the screen with a hole and a cross wire. So you'll have in the screen, you have the cross wire, a hole and a cross wire here, and then a source of light. So in other words, this object will be illuminated. So that's what we call the illuminated object. The cross wire has been illuminated by this bulb, so it becomes an illuminated object. So we are going to place the plane mirror at a certain distance away from the screen, and then we are going to adjust or move this convex lens between the screen. We're going to move it between the screen and the plane mirror until when a sharp image of the cross wire is focused on the screen, until when a sharp image of the cross wire is focused on the screen. So we're going to move this convex lens until when a sharp image of the cross wire is focused on the screen. Remember, light will be moving from this point. It will go to the convex lens, and then it will move onto the screen and then come back along the same path, and then it will form a final image, sharp image on the screen. So we need that sharp image on the screen, and when that happens, we shall measure the distance from the screen and to the convex lens. From the screen and to the convex lens, that distance is going to be measured, and that distance f is going to be the focal length of the lens. So that distance f is going to be the focal length of the lens. Let's look at method 4, that is using a thin lens, or what we call the thin lens formula, and an illuminated object, using the thin lens formula and an illuminated object. So in this method, we shall need an illuminated object. That means that we shall get our cross wires illuminated with a bulb, just like in this case. And then this time round, we shall have a different screen, not within the same object, but we shall have a screen, and shall place it at a certain distance away from the illuminated object. And then we shall get our our lens, whose focal length we want to determine. We shall get our lens whose focal length we want to determine, and place it at a distance u from the object. So just for illustration purpose, let me have this. So we shall have our convex lens placed at a distance u from the illuminated object, where on the illuminated object here we talk of the cross wires, and then the bulb illuminating the cross wires. Then after that, we are going to move the screen towards the convex lens or away from the convex lens. You can either move it towards or away, depending on how the image is being formed here. And then we shall move it until, in other words, we shall adjust the position of the screen until when a sharp image of the cross wire is formed on the screen, until when a sharp image of the cross wire is formed on the screen. And when we get that distance, when we have got that position of the image, we shall measure the distance from the screen up to the convex lens, and that distance v will be recorded. And then we shall repeat the procedure with different values of u. In other words, we shall change the values of u. That means that the distance from the cross wire and from the object, the illuminated object, and to the convex lens will be adjusted. If you had started with the 20, or if you had started with the 10, we shall go to 20, and maybe 30, like that. So we shall adjust that and change the position of u to a different value, and then we shall repeat the procedure and get the corresponding value of v, where the sharp image is formed. So we shall carry out this experiment until when we have different values of u and v, and then we shall tabulate our results in a table, including values of u, v, and then u plus v, including values of u, v, and then u plus v. And after that, we shall plot a graph of uv against u plus v. We shall plot a graph of uv against u plus v. So it means that uv will be on the y-axis, and then u plus v will be on the x-axis, and then we shall obtain a straight line graph whose slope is going to be determined. That slope s is going to be determined, and the slope is going to be the focal length of the lens. The slope of that graph is going to be the focal length of the lens. Let's look at method 5. In this method, we are going to use a thin lens formula. We are going to use the thin lens formula and then the method of no parallax. So this time round, we are still going to have an object. This time we shall not use a illuminated object. We shall use a pin object. So we shall get an object pin P1, and then we shall, so the setup will be like this. Shall get that object pin P1, which has been stuck on a cork, an object pin P1 which has been stuck on a cork. Then we shall mount our convex lens in that way on a lens holder, and then we shall place that lens at a distance u away from the object pin P1. Then after that, we shall get a search pin. We shall get another pin P2, which has still been mounted or stuck on a cork, which is now going to be called a search pin. We call it search pin because it is going to be used for searching the image, it's going to be used for searching the image of the object pin P1. So we are going to place that object pin. This is now going to be behind this convex lens, and of course your eye will be this side. Then we shall move or adjust the position of this search pin until when the image of the object pin P1 coincides with the search pin. We shall be observing that the image of the object pin P1 coincides with the search pin P2 by the no parallax method. When that has been achieved, then we are going to measure the distance from the search pin and to the convex lens. Still, we are going to pick the center point of the convex lens, here. So we shall measure that distance v, and then we shall repeat the procedure for different values of u, and then obtain the corresponding value of v. So if you had started maybe with 10, you can go to 15, 20, 30, like that, and then get the corresponding values of v. And then still, we are going to tabulate our results, including the values of uv, and then u plus v. And then we shall plot a graph of uv against u plus v, and it's going to be a straight line graph. We shall obtain the slope of that graph, and that slope s is going to be the focal length of the lens. Let's make some note. Let's make a note here. We need to make a note. Since no measurements need to be made on the surface or on the surfaces of the lens, this method, that is this method 5, can be useful in a number of cases. That is when finding the focal length of a thin lens, or when finding the focal length of a lens, or a lens that is inaccessible, when getting the focal length of an inaccessible lens, such as a lens which has been fixed inside an eyepiece of a telescope or a tube. For example, if you have a lens which has been fixed in a tube which cannot be seen, or let me say which cannot be accessed. You can't measure its a distance from the surface up to where the lens is. We shall use this method. So that's getting the focal length of an inaccessible lens. So that's why this method is very, very useful. Other methods we shall be discussing in the next lesson. We have other methods still for determining the focal length of the convex lens. We shall look at those methods in the next lesson. Yeah. So thank you for your attention. We meet in the next lesson.